Hey everyone, and welcome back to this class, Advanced Convolutional Neural Networks. In this lecture, we're going to do a quick review of CNNs, just in case you need to get up to speed. What I'll assume in this lecture is this. Number 1. You already know how to write a feed-forward neural network using some library. Number 2. You already know generally how a neural network works, how to train it on data, what data looks like, or in other words, what format it takes, and how to make predictions. And number 3, you already know about convolution. We are definitely not going to go over convolution from scratch in this course, because we already did that in the last course. So if you find anything in this review confusing, or you need more review, remember that this is just a review, because the rest of the course isn't just dependent on you knowing this stuff, but also having experience with it. So just as an example, since I know you guys love examples, you can't walk into a quantum mechanics class and ask them to teach you Newton's laws. And even if they were nice enough to review Newton's laws, that still wouldn't be enough for you to learn quantum mechanics. You're not going to learn Newton's laws this afternoon and then start learning quantum mechanics tonight. This stuff takes time, and it's the experience that matters. That means using your brain to think and ponder about the subject, and doing the exercises and so on. So let's start this by doing a quick review of convolution. This is a picture of convolution. The big square is the image, and the small shaded square is the filter. The filter is a weight matrix or tensor, where the weights are learned by backpropagation. This is a common mistake with students, by the way. They assume that we designed the filters somehow to be edge detectors or something. But of course this is deep learning, and the programmer never designs any of the weights. Everything is learned by backpropagation. There can also be thousands of filters in a neural network, so there's no way you could design them all yourself in a scalable way, even if you wanted to. So what is this doing? Well, the filter essentially slides over every possible position on the image, and each time it does that, the overlapping parts get multiplied element-wise and added together. That's all there is to convolution: multiplication and addition. Now conceptually, we know that this is sort of the equivalent of a matrix dot product, and we know that a dot product is conceptually like a distance measuring technique, or in other words, it measures correlations. So if the filter is very correlated with this piece of the image, then it's going to output a very large number. If the filter is very different from this piece of the image, then it's going to output a very small number. In actuality, what we call convolution in deep learning is actually more correctly known as cross-correlation. So for some people, this is a really helpful analogy because convolution can seem like a weird exotic concept. But really what you're doing is just going over every part of the image and saying, hey, how correlated are you to this filter? That's pretty much it. Once you know about basic 2D convolution, we can start to talk about convolution over 2D images that have depth. We know that color images are usually represented with the RGB color channels, so an image is represented as a 3D matrix, height by width by color. But you also have to be careful about what library you're using. For example, if you're using Theano, then the color channel comes first, so it'd be color by height by width. In this course, we'll be using Keras, which does have a Theano backend, but we'll be using the Tensorflow ordering convention, where color comes last. So how do we do convolution when we have a 3D tensor as input? Well, it's still a 2D convolution. We still slide the filter across the image, just that the filter also now has 3 color channels, so you can think of it as a small box instead of a small square. But the operation is the same. We slide the filter over every part of the image, multiply everything in the 3D box element-wise, and add them all together, and we get the output. The weird thing about this, though, is that the output is a 2D image. And that's because we still have one more piece to add. So to speak in more general terms, images are not just height by width by color, but height by width by feature maps. We can think of the color channels as the initial feature maps, but deeper into the CNN, they no longer represent different colors, but different features. So a full CNN filter is actually 4-dimensional. We can say it's C1 by height by width by C2. Again, what order these dimensions are in are dependent on what library you're using, but at least in these theory lectures, I'm going to use the convention that C1 represents the input feature maps, so it goes in the front, and C2 represents the output feature maps, so it goes at the end. The key part is that the input image is of size height by width by C1, and the output image is of size height by width by C2. So images in a CNN are always 3D, where the third dimension is feature maps or color. Now that we've talked about convolution, what does a full convolutional neural network look like? Well, the standard architecture, inspired by the original LeNet, is basically a series of convolutions followed by a series of fully connected layers or dense layers. We also add pooling, which can be of the max variety or the average variety, to downsample the image after certain convolutions. So a standard architecture would be like this: conv, max pool, flatten, dense, and then a final dense with softmax. One of the general patterns we have in a CNN is that after each convolution, the image generally gets smaller, but the number of feature maps increases. So we shrink the spatial dimension, but we increase the feature dimension. Conceptually, you can think of this as the neural network learning to represent more abstract features of the original image. This is going to be a really important concept in this course, so it's worth exploring more. One of the main successes of CNNs is their interpretability. Researchers have shown us a pretty intuitive result. Each layer of the CNN learns more and more complex features of the input. At the beginning, we just have these basic edges, but by the time we get to the end, we're looking at macro objects like facial features and so on. This makes sense because every time you pool or do a convolution with a stride of greater than 1, you shrink the image, but the filters generally stay the same size. So the filter is effectively covering a larger part of the original image after each step, allowing it to find bigger and more complex features. We'll see this theme repeated throughout the course. In this course, the main library we're going to be using is Keras. The big question some of you might have is why? In the past, we've always used lower-level libraries like Theano and Tensorflow. Well, it has to do with levels of abstraction. As an extreme example, that's why we are not writing code in assembly or C. That's way too low level for us, given that we're interested in a much higher level concept. Actually, as a side note, many people actually do write machine learning algorithms in C. It would just be prohibitively painful for us because there would be too many irrelevant details. So the next level up might be Python, and then Numpy, and then Theano and TensorFlow. And if you recall, we actually did write neural networks in Numpy, but there's a level where that gets too cumbersome. In the study of CNNs, we wrote convolution, and we wrote CNNs in Theano and TensorFlow, because it taught us to pay attention to how they worked. But at this stage, we already know how they work, and that's no longer what we're interested in. Now what we want to know is how to use them within larger systems. And so we take the abstraction up one level again to Keras. The goal is to be writing in the ballpark of hundreds of lines of code per exercise. In this course, if we were to use TensorFlow or Theano, we'd be getting into the thousands. Whereas in previous courses, if we had used Keras, we'd be in the tens or even less. So the idea is to always try to stick to hundreds of lines of code. Basically, what this means is this. Number 1, we no longer need to write our own layers. Number 2, we no longer need to write down the gradient descent update rules like we did in Theano, although they already come built in with TensorFlow. And number 3, we no longer need to write the training loop for batch gradient descent. This is both very long and repetitive. So with Keras, all that stuff is written for us. You can imagine if you're trying to learn how CNNs work, and the solution is just a function called makeACNN, you're not really learning anything at all. So that's why we avoided Keras in the past, but now it's the perfect abstraction. If you don't know Keras, it's extremely simple to learn, so you'll at least be able to pick it up in the next example. I'll walk you through the code, but there are a few more files in the repo you can look at to get a better feel for how it works.